As an astronaut, I have 3 dreams. The very first dream is to fly actually to space. I already achieved this dream. The second dream was to open the door of the space station and to walk freely in space.
Thanks for watching over.
And the third dream that I hope to fulfill is to fly to the moon, to step on the surface of it and to explore it. And the next time we fly to the moon, we want to stay there for an extended period of time.
But the moon is a harsh environment. We have radiation, we have a vacuum, we have large thermal swings. We even have micrometeorites coming in from space every day. So the first thing we need to do is create some shelter just to be able to survive on the moon. It's just about survival.
We want to set up a moon base before we can fly to planet Mars.
So we had a dream of making a competition and inviting the best people in the world, saying, please show us how to 3D print with materials from the moon and Mars.
What's interesting about space architecture is you're experiencing the most extreme version of what you do for a living.
How we actually design for a community that lives in a completely internalized space.
Because the minute you step out in Mars, like as humans, we would die.
It's kind of moving back to caves. You know, you really want to live in caves. You want to have some mass around you.
The functional challenges are so extreme. They really force you to think about how to extract beauty from the least amount of material, from the least amount of energy, in the smallest space possible.
You send the machine, okay, and the machine can build multiple houses.
We can create really large structures, but with small robots. It's a bit like termites would build a termite nest.
Then that machine can keep on going and keep on building.
You might need a big restaurant. You might need a large gym. You might need a bar.
So you can actually think of bases, you can think of colonies, you can put buildings where they need to be.
We started with the design of a space station made up of modules inspired by organic models. We've got flowers, leaves, so there's really this idea of a connector and petals that will develop around it.
Why astronauts are supposed to just survive in space? Why they can't just thrive? Why space can't be as beautiful as their own homes?
This is the first times in history that you really get NASA scientists and engineers collaborating with architects, which is making this round of space exploration much more interesting than the Apollo era.
Humans can't exist for their lives in cold, sterile, machine-like spaces. Without beauty, I don't think we are going to be able to move beyond.
Confirm ignition and the thrust is go. Roger, 11, we'll pass that on, and it certainly looks like you're well on your way now.
Next phase of the NASA program is the Artemis program. And this is where we go back to the moon, the next man and the first woman, and we will go there to stay. But the moon is a harsh environment. So the first thing we need to do is create some shelter just to be able to survive on the moon. It's just about survival.
This is Apollo Control, and we're showing orbital weight now, 138,892.9 pounds.
Cut off.
My name is Rob Mueller. I'm a senior technologist at the NASA Kennedy Space Center, Swamp Works. I've been with NASA for 33 years. We're in a high bay. It's a historic high bay. This is where the Apollo astronauts trained to go to the moon. So we stand on the shoulders of giants. It has a lot of history. But now we're doing it again. We're going to the moon, and so we have a simulated lunar surface behind us. And we have to be able to go out and train in this very dusty environment. And so every day in our lab, we can just walk on the moon. I don't think it's practical to launch concrete and beams of steel into space. When we go to the moon, the whole idea is to bring nothing from Earth and use everything locally. This is a simulated lunar surface. It's exactly like standing on the surface of the moon. This is the regolith, which we need for construction material. It's very dusty. This is what the moon is like, and we have to deal with this dust every day on the moon. But we need a machine to get the regolith for the construction feedstock, the concrete. So this machine is a machine that we invented, which will dig up the regolith.
We confirm ignition and the thrusters go.
It collects regolith in these scoops, so when it turns one way it digs, when it turns the other way it dumps.
35,570.
Once we have this regolith, we can turn this into a construction material. We mix it with plastic and then we extrude it through a 3D printer.
Houston, Apollo 11 and gave us a magnificent ride.
A 3D printer, you take this material here and you put it in here. And then these are heaters. And he heats this material and it extrudes the material layer by layer by layer. So you can see we built these layers. And it's very strong. And then what's really interesting is we took the excavator that I showed you and we excavated the regolith. And then we put it in a 3D printer and we made a wheel for the excavator. So now we have the excavator getting the regolith, putting the regolith into the 3D printer, and it makes a part for itself. So it's the first step to a self-replicating robot. The exciting thing about this technology is we could do this today on the moon. And we can bring a machine like this, and then we can make this material on the moon today already, and we can use a robot to 3D print a large structure on the moon. NASA is full of engineers. Many, many engineers, all kinds of engineers. But engineers, they build products and they meet specifications. 28.6. So we had a dream of making a competition and inviting the world, inviting the best people in the world to this competition and saying, please show us how to 3D print with materials from the moon and Mars. And we did that. We organized something called the NASA Centennial Challenge. And the challenge was to take the local materials and turn them into a concrete type of construction material. And this has never been done before. So we were looking for the teams to come up with novel, innovative solutions. What we found was the architects, they had another dimension on this problem. They said, we want the human element to be involved. We want the humans to be happy. Is this structure, is the function good? Is it a beautiful structure? Is the aesthetics nice? Does a person feel good when they're living there? So these are the kind of ideas that architects bring to the table that engineers don't bring to the table. We had points for a minimum human intervention. So if it's completely automated, you get more points. And so we had the competition, 180 teams showed up, but only 2 were able to actually do the printing. The final 2 teams was Penn State University and a company called AI Space Factory.
I've always been fascinated about space. So the NASA competition was really an opportunity where I could apply my skills as an architect to this problem of how to build on Mars. But for me, the bigger challenge is actually working on the technology to make it real. I'm David Malott, founder and CEO, AI Space Factory. I've been an architect for over 20 years. My focus has been building skyscrapers. It's recently that I started exploring the challenge of how to build in space. Obviously, Mars is a very different environment from Earth, but the skills and principles which I've learned by building skyscrapers on Earth translated fairly well to the challenges of building on Mars. You just have to understand a different environment, a different application of physics. Just for example, a skyscraper on Earth, we design it for the wind. And on Mars, we designed our habitat to contain an internal air pressure. So the ideal shape in that scenario is something that's very round, without sharp corners, so that you're not creating any stress on the structure. So essentially we found the most structurally optimal shape was this egg. You know, from that point is really about how do we just make it feel like it fits on Mars a little bit. So there's some details like the way that the structure comes down to the ground and it flares out a little bit, which is inspired by the silhouette of a penguin and the penguin feet, just the way that kind of belly comes down and you get the feet. And it just personifies the design a little bit, so people can relate to it. We called the Mars habitat Martia. We gave it a name, again, so people can relate to it and they begin to feel a kind of attachment to the design. So the NASA Centennial Challenge started with the design phase, but the second part of the challenge and the much harder part of the challenge was to build the prototype. It's a 1:3 scale Martia, so it's not as big as the full one, it's a reduced size, but nonetheless it's a huge challenge. One of the tests that NASA performed after we printed the Martia prototype was to crush it with a Caterpillar excavator. This 40-ton excavator comes, puts the big scoop down on the top of the structure and attempts to push it down. And we were watching it and we were shocked because the structure was stable and then the treads of the Caterpillar actually lifted up off the ground. So that's how strong the material was, and that's how optimized the shape was.
First place goes to Team AI Space Factory. So.
Beyond these technical challenges and the basic need to survive physically on Mars is the mental toll that we think it would take on an astronaut.
Once it has changed, that will be the go for Kayla to complete some of those tasks in location.
And keep in mind, an astronaut will have been in a very confined space capsule, hurtling off to Mars for many, many months before they even arrive. So Mars is designed to be a home. So we made every effort we could to open up the space internally, to create lines of sight between floors so that you don't have this sense of confinement. And then that's sort of where, say, the beauty of the design comes into play, where we really think of how to craft the interior space, how to bring in light. So that affects the mental well-being of the astronaut, which is equally important when you think about how long they're going to be there. I tend to design with the second person in mind, so it's not for myself, but to put yourself in the shoes of the astronauts who would actually be there and what it is that they would need.
European Space Agency. We get currently 3 flight opportunities and 6 candidates, which means I would see like a 50% chance of me flying towards the moon. My name is Matthias Maurer and I'm an ESA astronaut. I launched on the 11th of November 2021 to the International Space Station, and I stayed there for around 6 months, and I came back in May 2022. On the International Space Station, we wake up every morning between 6 and 7:30. Then we work until 6 or 7:30 in the evening. Hours of working day. We have 1 hour of lunch break. Kitchen is an important place where you come together. Usually you sit around a table. In space you float around a table. And you feel relaxed. You will be in a mood to talk, to enjoy the good food. It also has a very important social aspect. So it is important to have such a room that looks less operational and more like homey style. 2.5 hours of sports session. And at the evening, at 7:30, our day ends again with an evening discussion with the ground where we summarize how the day went and to have an outlook on the next day. Most of the time I spend obviously in my cabin, in my bed, sleeping. It is in the Columbus module, which we see here. It was the area where I worked and slept. Well, my favorite spot on the International Space Station was a place called Cupola. It's our window to the universe, or in this case, the window towards our planet Earth. And we have a 360-degree all around and can observe not only the planet below, but also the area, the atmosphere, and the part of the night sky that we can observe. What I missed in space most was something of the color green. It's green vegetables are difficult to conserve, and so most of the food that we have is without color green, and we don't have many plants. Only a small greenhouse that occasionally we had a small experiment, had some elements of color green, and looking out of the window we see the rainforest of planet Earth. But the rest around us, as you see it, it's white, it's technical, it has cables, it's metallic look, but the color green, which for me is a synonym of nature, is what I missed most.
As a little girl, I was often in my own world, my own bubble, a bit isolated, not always accepted at school either. And so I imagined my own worlds. And in those worlds, there were worlds where we lived on other planets, in bubbles surrounded by vegetation. So I was very passionate about nature. I collected my little leaves, I had little herbariums. I learned a lot about the species on Earth. So there was this vision. In fact, it's quite funny to see how you end up doing what you dreamed of as a child. I'm Barbara Belvisi, the founder and CEO of Interstellar Lab. To support a group of 4 astronauts in a closed circuit, with some of the food coming from the freeze dryer, a 55 square metre greenhouse was needed. So it's an inflatable, portable structure that we can set up on the surface of a planet, be it the Moon or Mars, and install all the systems to grow the plants. We started with the design of a space station made up of modules, inflatable modules that we would plug together. They're what we call biopods, linked by connectors. And in fact, this concept of the station is inspired by organic models. We've got flowers, leaves, so there's really this idea of a connector and petals that will develop around it. And so on Mars, when faced with sandstorms and strong winds, this elliptical shape will give it a certain aerodynamic quality that will make it very resistant to the strong and violent winds that will come. The most important thing for the astronauts when they're in space is the time they have to spend exploring. Take the lunar base. It's more important that they spend time exploring its surroundings and gathering things than doing maintenance on the greenhouse. So we work a lot with this logic of automation and having a greenhouse that's intelligent and self-learning. We're in the biopod, inside the first biopod built. Right now it's roughly 25 to 26 degrees and the humidity must be around 75%. It's a rather tropical climate. We're currently growing 12 species inside the biopod. Here we have, for example, the Madagascar periwinkle, and here are baby Madagascar periwinkle plants, because we've already completed a first growth cycle. We always use aeroponics. There's a system of nozzles that spray extremely fine droplets of water mixed with nutrient solutions. We really accelerate growth, so that in less than 3 weeks we have an adult plant with flowers. Here we've got vetiver, here patchouli, and here passion fruit. We're also working quite a bit on mushrooms that will make up for a lack of vitamin C. Everything's completely edible without needing to be treated or re-cleaned or anything. There's no operator controlling the biopod. It will, by itself, recreate climates, activate or deactivate the ventilation, capture CO2, treat the water, all according to its needs. So we're working to optimize the astronauts' time during future missions on the moon. I'm often asked the question, will we make potatoes on the moon like in The Martian? Well, the potato isn't the best candidate because it creates lots of roots. We eat the potato, but then there's all the green waste, the leaves that we don't eat. In fact, we have about 10 criteria that will allow us to make a pre-selection of plants that we'll send, but it's not yet finalized. We need to be ready for the lunar greenhouse by 2027. We've got a few adjustments to make to the materials and the watering system for the plants, because gravity is very different on the moon. So by 2027, we aim to be ready and to have actually adapted the biopod to lunar conditions, so that we can fly on the Artemis missions.
3, 2, 1, and liftoff of Artemis 1. We rise together, back to the moon and beyond.
The new phase of missions are called Artemis missions. Currently we have 3 different destinations. The first will be the gateway station flying around the moon. The second one will be the moon, where we land. And there we build a station, and on this moon station we will test everything, develop everything that we will need before we can fly to planet Mars. Artemis Mission 1 has already proven successfully to fly around the moon without astronauts. The mission Artemis 2 will already see the first 4 astronauts flying around the moon in the gateway station. Artemis 3 and 4 might already be landing missions when the lander is ready. The gateway station, it will not fly with a space shuttle, as Columbus has been transported by a space shuttle to space. And so the diameter of the gateway modules will be smaller than the modules that we see currently here. So smaller than the ISS modules. Six months in space, you can live according to the standard of the ISS without any problem. I even had colleagues up there who stayed for 1 year, and they looked happy and they could adjust to the environment. I don't think that the gateway station would be big enough, comfortable enough maybe to spend also a year. But even if the gateway station will not be as cozy like here on the International Space Station, it still will be a step forward for humanity.
Both hands down about the fourth rung up. There you go. I guess you're about the only person around that doesn't have TV coverage of the scene.
The Apollo missions landed on the equator of the moon, and they were always planned and designed to be short duration missions. So the longest mission that we had stayed there for 3 days and had 3 spacewalks on the surface of the moon. The next time we fly to the moon, we want to stay there for an extended period of time. So we will bring a pressurized rover where we can live in for even up to 1 month. We drive the rover from one area to the next area where when maybe the next crew can land and continue the exploration. So we want to explore a much bigger area of the moon, and we also want to go to areas that the Apollo astronauts couldn't fly to. And in the long run, we want to set up a moon base. Here, the Columbus module, it's a smaller module, but even in space, this smaller module, it becomes so much bigger than I feel it like right now here on the ground, because I can use it in 3 dimensions. I can work on the roof, I can work in the angles to the left and top, and can float around. And so it feels for me much bigger than it feels to me here on the ground. It will be different once we arrive again on another surface on the moon, when again I cannot use the ceiling or when I need to walk on the ground like here on planet Earth. Then I would need more volume. A station where we will have working areas, where we'll have living areas, and where we also have a greenhouse, sports area, and a kitchen area, and sleeping area. So everything that you need to have a life similar to the one that you have back home.
We wanted to make something which would really visualize what it felt like to go from Earth all the way to the moon, and then, to settle there and to live there. We were searching for something that would express the new era of space exploration. And I think that it's hard to capture the experience of space unless it's cinematic. There's something profound about the act of being on the surface of the moon, so to just see that visualized was incredible. So I'm Colin Coote. So I'm an architect. I practice at SOM here in New York City. Honestly, I do all sorts of buildings, everything from universities and research facilities to workplaces, skyscrapers, train stations, airports. ESA, they were looking for someone to help them imagine the Moon Village, which was the creation of Jan Werner, who was the Director General of ESA. And we were very interested in trying to look at the incredible technical aspects of designing in space. And so we started to work together and formed a partnership fairly quickly. So I led the design team in the design of the Moon Village, and so, you know, an architect's role is really to bring a creative vision to the process of design, but also to rely on the expertise of the consultants and the engineers around you. So we work very closely with ISA and their engineers. We have our own engineers here at SOM. And the job of an architect is really to resolve a tremendous number of functional constraints to make it work. People are very accustomed to science fiction, and science fiction, you know, takes a tremendous amount of liberties with what space is actually like. You know, from the start of this, we were determined to make this a realistic depiction of the experience of what it meant to sort of transcend the surface of the Earth. And to do that, you really need to sort of see it and experience it in real time. So the film really tries to sort of capture the realities of space, you know, the low gravity realities, the darkness, the constraints of designing. As an architect, what's interesting about space architecture is you're experiencing the most extreme version of what you do for a living. You try to take the patterns of living and give it form and make it beautiful. The functional challenges are so extreme. They really force you to think about how to extract beauty from the least amount of material, from the least amount of energy, in the smallest space possible. And I know ISA uses it a lot to talk about what they do to the general public and try to communicate, you know, what their mission is and the role that they can play in the ongoing, you know, settlement of the moon. This is Tower 1. I was part of the team that designed it, yeah. I was a younger architect back then. So this is the model. And if you look out there, you can see a construction crane. It's in the green terracotta. There's 2 buildings. Sometimes you'll look out here and it's incredibly beautiful. Sometimes you'll look out here, you'll see a lightning strike on a skyscraper on a rainy day. Sort of places you more in the larger cosmos than when you're on the sidewalk. So the siting was critical. It was a key first step of the project. And if you think of the moon, you know, it has a 28-day cycle. 14 days it's in the sun, 14 days it's in darkness. So over the course of the 28 days, you would go 2 weeks without any ability to generate energy. So you're looking for a site where the sun is constant. And to do that, you have to look at the poles, the North and South Pole. There's a tremendous number of craters at the South Pole. Those craters are incredibly deep. And because those craters have high rims, if you land and place your settlement at the top of the crater, the sun never sets. It moves around you on the horizon line, but you get 24-hour sun all day long, which is perfect because then you can have a consistent source of energy. So we were looking at the Shackleton crater. There's a small portion of the rim of that crater which is rather flat and able to be landed on. And so that was the site that we chose. The concept of the Moon Village, the idea of a permanent settlement, means that you're living there for incredibly long durations. And when you do that, you have to start to think about the well-being of the human. And humans can't exist for their lives in cold, sterile, machine-like spaces. They need beauty. They need spaces which replenish them. They need spaces for stillness, for quiet. They need spaces for community, for conversation. And the architecture has to form that around them. Without beauty, I don't think we are going to be able to move beyond the surface of the Earth. Contemporary space architecture is very defined by how you get it to space. So you have to put it in the payload of a rocket, and it has to fit there, and it has to be lightweight. And once you're in space, you immediately are sort of confronted with the realities of being in a vacuum, and so it has to be structurally sound as well. And most capsule architecture is metallic cylindrical shell. It's what you see on the International Space Station. But there are sort of new forms that are being investigated which are inflatable. And what that results in is you can, expand the area by 40 or 50% once you're in space, but you also have a completely structural free environment on the inside. The inflatable capsules also can be deployed vertically, which means you can have different floors within them, which is also really ideal. If you think of the International Space Station, it's essentially one long tunnel. And to get from one place to the next, you have to go through everything. The beauty of separating uses is something very intrinsically important to how humans go about their day. You don't have that on the International Space Station. You have to have that on a permanent settlement. I think that the more that the science advances in the last few years, the more that it appears like some combination of capsule architecture and 3D printing regolith is going to be what the first settlement looks like.
When you move to another planet, you need to pack light and compact. So that's why a lot of our designs are built out of inflatables. But once we move away from Earth, we have a lot of radioactive radiation hitting our astronauts. So we need to 3D print big shell structures, these kind of protection shields around our habitats. It's kind of moving back to caves. You really want to live in caves. You want to have some mass around you to protect yourself from all that radiation. Well, welcome to our studio here. This is kind of where we do most of our design, in this studio here in London. Let me take you a little tour of what we have here. So a while back we did a project for a competition for NASA where we designed a 3D printed habitat. So we have, a big inflatable habitat with 3D printed furniture. Besides images, we also love to work with physical objects. All of these are 3D printed. Here you see some of our kind of 3D printed pods, and this here really is a new type of lower Earth orbit station. So the International Space Station is going to be retired, and there will be commercial space stations. So this potentially is one of them. Have a little moon, because we're designing a new base for ESA. This is actually the bar for a moon base, because if we have 150 people, of course they want to have a bar. But what about sports? If you're on the moon, suddenly 1/6 of gravity, we're all going to be like a superstar free soloing rock climber. If you have a greenhouse in orbit, the plants can grow in all directions. Space tourists, well, they might be quite rich, these space tourists, so what might they want to be doing? A bit of gambling. So could it be a casino in space? Or what would that look like? So really start to think like what kind of new potentials and new things we could start doing in space where we have less gravity. I'm Xavier de Kesselier. I am Head of Design and Head of Innovation here at Hassel Studio. NASA asked us to design something that was fully 3D printed. I mentioned before that you need to pack light and compact when you move to another planet, right? Because it's very expensive. Normally when you have a 3D printer, the 3D printer is bigger than the thing you want to 3D print, right? That would be very silly for us to bring a massive, massive 3D printer to Mars. Right? So we rethought that idea of a printer. And we didn't think of it as like a big machine, we thought of it as lots of small machines. ants. It's a swarm of small robots that can pick up some regolith, some Martian dust, bring it to site, dump it, lay it down, and then another robot comes and kind of solidifies it layer by layer. So that way we can create really large structures, but with small robots. We call it swarm robotics. It's a bit like termites would build a termite nest. But the problem with these robots was that once they were done their job, I couldn't reuse them. And I was like, well, that's really wasteful. You know, we just moved to Mars and I'm already going to have a whole bunch of robots that are for the bin.
I'm sorry, Dave. I'm afraid I can't do that.
We need to do something else. So what we did, we redesigned all the robots and we made them very modular. We made them like Lego, right? So we only have different types of parts, like I have a wheel, a battery pack, a digging part.
Open the doors.
And the robots can actually reconfigure themselves. They're modular, they can reconfigure themselves for different tasks. So once they've finished printing the building, they can actually reconfigure themselves for other types of uses. And there's a huge redundancy with it. Like if I just have only half of the parts that arrived, that's okay. You know, we'll just have less robots. It will just take a bit longer. It's a bit like with a termite nest. If I would take half the termites away, the termite nest still survives. It might be a bit less efficient, but it would still work. We didn't win the NASA competition for a very good reason, because we actually were a bit naughty. We didn't actually follow the brief 100%. The environment where the astronauts will be living in, the pressurized volume, also have to be 3D printed. Now we thought that wasn't a good idea. We actually thought it would be much better to have prefabricated these inflatable elements, these bubbles where the astronaut would live in. It's made on Earth, it's not going to leak. We've tested it, we know it works. And then we only 3D print the shell structures on top of those that are there not to keep the air in, but to protect them from radiation. So we had like a two-way system, right? Where we had like a prefabricated part and a 3D printed part. You know, it was in the brief that we had to do it fully 3D printed, but we actually didn't believe in it. We actually still believe now that having this like two-step approach is the right way to do it. Here we have the physical model of the project. It's a sectional model. So we show this kind of shell structure that would of course cover everything. This is a lab, but this is for example a kitchen. We have a workbench over there. We have the greenhouse. 6 different functions, 6 different bubbles. Then we have in between, we have smaller ones. In the small ones we have the life support. So all the oxygen is kind of generated there, the water recycling all happens in these small bubbles, and they service really the larger ones. Now, the small bubbles have 3 exits, or 3 doors. We have one going to the bubble on the left, one on the right, and one to the outside. And the one to the outside can be either for suit ports, so you can get the astronauts really to kind of get out and do an extravehicular activity. Or some of them actually connect to a rover. The rover really connects back to the base right there. So your astronauts can really go inside and then they can just go and explore the Martian surface. And if we look outside here, what we also see is all our rovers. So all these rovers and these robots, this kind of modular system of robotics, that were the ones that really printed this shell structure. So we have about 6 astronauts here, but we think it would actually house up to 12. So some of the rooms are single rooms, but we think we can put a bunk bed in so they can actually double up. So the pods are really organized in a circular organization. The reason for that is, imagine, right? Something really bad happens and there's a leak in one of the pods.
Sorry, Dave.
So they need to evacuate this pod really, really quickly. They can go left and right, they might be able to close it off, but the door's here. Interestingly enough, if this one falls away, they can actually still access every other pod.
Open the doors.
An earlier design process, but it was in a star shape. The problem with that one is then if the middle pod fails, people would get stuck in certain parts of the base. So the circular design it's really for an evacuation reasoning. The cave itself would take about 3 years to build. So all this that sits underneath only comes with the astronauts. So when the astronauts come, they only have this shell structure that is there, like an empty cave for them to move into. So here we are in the real thing, right? You've seen videos, you've seen renders, you've seen a physical model, but this is the mock-up, right? What we have here is an inflatable, right? It's an inflatable structure that will keep the atmosphere for our astronauts. This is the breathable atmosphere that our astronauts can be in. And we can look outside, we see the rest of the habitat. So we're really underneath the shell structure that protects us from the radiation, and further there we see more pods. So we're only in one of the pods, but there are actually 6 of these pods. All of this furniture that you see here is made out of recycled plastics. We can imagine the astronauts having waste plastics from food or from experiments, right? From science experiments. So all the furniture here is made out of recycled plastics, and the way we make it is we 3D print it. This furniture might look very spacey, right? And this kind of like very organic form, but the reason for that is that it's really been printed on its side, right? If you look at it here, this is all printed out of one kind of bead of plastic. Almost think about it as toothpaste. You would just kind of squeeze it out layer by layer, layer by layer, and that way you can really create this chair, right? It's like a chaise longue, really. So in a way, the more they recycle on Mars, the more furniture they can have. The materials that we use are not just all plastic. Maybe on Mars we would have some thin veneers. Why not? So we really believe that it's kind of working with different materials that we currently are. You know, if you look at the International Space Station, it's all very cold, it's all metals. But we believe that to live for a longer period of time on another planet or in space, we need to go back to the materials that we used to living with. Look at now at the International Space Station. I'm not sure if you've seen the internals of it and how the design is. It's quite a mess. Laptops, Velcro, wires, all sorts of things. Does anybody live in this space? You know? And I still don't understand why astronauts are supposed to just survive in space. Why they can't just thrive? Why space can't be as beautiful as their own homes?
I hope before the end of my life I'll be able to go to the moon. In fact, I think many people will be able to go in the next 15 years.
Even if what we do, even if, like, say, what Space Factory does now doesn't get us to Mars, I think we've set out that vision and we've started those initial steps. And if it's the next generation, say my son's generation, that picks up the mantle and are the ones to actually achieve it, that's the perspective that we need when we approach space and the challenge of building on another planet.
I think that the Moon Village and the first Mars Village will be just like on Earth. There will be many different kind of buildings. So there is no one design that will dominate. In the end, you will have much more diversity, many different designs, and we will learn. As we go, we will learn, and things will improve, and we will adapt.
There's a great quote by Igor Stravinsky. He gave a lecture at Harvard, and it's about looking at a blank sheet of paper as a composer and being paralyzed because you don't know which sounds to make. And then he gives himself constraints. And he talks about, you know, it's going to be a symphony and it's going to feature the violins. And every constraint he adds makes him more creative. And he talks about the beauty of constraints on a creative mind, and I firmly believe that. The more constraints you have, the more creative the result.
Right on